In our last lecture, we discussed about the Biot-Savart law, and we also did a quick analysis by comparing the Biot-Savart law with the Coulomb's law that we had studied in the first chapter. Today we'll take our discussions a little further, wherein we will consider a bit of a complex shape in addition to the simple element that we considered the last time when we were exploring the Biot-Savart law. So today we'll try to determine the magnetic field on the axis of a circular current loop. So what we are assuming here is that we have a circular loop through which there is current flowing. And obviously when we have current flowing through a circular loop, you'll expect it to also generate a magnetic field. And we are interested in trying to determine what's the magnetic field along the axis of the circular loop. So we'll keep the case quite simple. It is the magnetic field that we wish to determine along a random point on the axis of the circular loop. So let's assume a circular loop. So let's assume a circular loop which is on the YZ axis. So if I consider my three axes, so this is my X, this is my Y, and Z axis is the axis that is coming out of the plane of the board. So it is coming out of the plane of the board. So this circular loop is along this axis, right? So due to constraint of 2D space, you will have to visualize the 3D image of what I am drawing on the screen. So let's assume it has a center O and there is the axis that's passing through the center. So I have placed my circular current loop in such a way that the center of this loop coincides with the center O of the three coordinate system. So I have placed it in such a way so that this center of the circular loop is exactly on the center of my three-dimensional coordinate space. Now I'll assume that the radius of this loop is a capital R, and I am interested in finding the magnetic field, let's say dB, at a point A which is along this axis. So if my loop, circular loop, is on the YZ axis, on which axis do you think is this point A? Yeah, you guessed it right. It is on the x-axis. It will be on the x-axis. So this distance along the x-axis, I will assume it to be some x, small x meters or small x units. Now I am interested in finding out the magnetic field at this point A. Now if I want to take advantage of the Biot-Savart law, I'll have to consider a small current element, let's say at this point. So I'll take a small current element of length dl. So my current element will be IdL because there is current I flowing through the loop, and I am interested in finding out the magnetic field at point A, which I will designate as dB, due to the small current element IdL. So Biot-Savart laws, yesterday if you recall, we gave the statement of Biot-Savart law as the magnetic field being directly proportional to the current element and the vector product of it along with the displacement vector and inversely proportional to the square of the distance between the point of interest or the field point and the current element. So we'll assume this distance between the point of interest or the field point and the current element to be small r. We'll assume it to be small r, and if these are some of the assumptions we start off with, then by Biot-Savart law, what do you think the value of dB would be? So dB, you know, we arrive it as mu naught by 4 pi into I into the vector product of dl and r by r. Now to find the vector product, we are interested only in the magnitude over here, so we'll have to resolve the vectorial form, in which case this will get converted to I, this will get converted to r into dl into sine theta by r cube. Now what is theta? If you recall from the Biot-Savart law that we discussed the last time round, theta was the angle between the tangent to the current element and the point of interest. So now if you just closely observe here, this current element that we have seen is in this plane. It is in the YZ plane. So the current element is somewhere here. So the tangent is coming out of the board, right? Whereas the point of interest is in the XY plane. It is somewhere on the board over here. It's in the XY plane. So if I consider this loop, half the loop is outside the blackboard and half the loop is behind the blackboard. In which case point A is directly on the blackboard. So if you see, the tangent to the current element is in this direction, whereas the point is in the x-axis. So these two planes are perpendicular to each other. So this theta is equal to 90 degrees. So sine theta resolves itself to 1, in which case this now reduces to mu naught by 4 pi into I r dl by r cube, which is further resolved into mu naught by 4 pi I dl by r square. So this r square, if you observe the figure, by Pythagoras theorem, r square is equal to x square plus capital R square. So I can rewrite this as mu naught by 4 pi into I dl by x square plus R square. Because of the simple reason that r square is equal to x square plus r square by Pythagoras theorem. Now, so we have now resolved that dB due to the current element ideal is given by this right hand side, mu naught by 4 pi into I dl by x square plus r square. Now remember, we are not interested in the field, magnetic field at point A due to one current element. We are interested in the magnetic field at point A due to the entire circular current loop. So we have to take this discussion a little further. But before we take it further, now in which direction do you think this magnetic field dB would be acting in? What would be its direction? So from Biot-Savart law, dB will be acting in a plane perpendicular to the plane that is constructed by taking the current element and the displacement vector r together. So the current element is somewhere over here, if you recall the 3D figure, and the displacement vector is in this direction. So if you take these two together, this is the plane that I am talking about. The board is the plane I am talking about. So if this is the plane in this direction, then my field dB at this point A will be perpendicular to the direction of the displacement vector. So it will be at 90 degrees to this displacement vector, making an angle, let's say phi, with the x-axis. So this will be the direction in which dB will be acting. So to take the discussion further, I will split this dB into two components. One along the x-axis, which I will call it as dBx, and the other I will split it along the perpendicular direction to the x-axis, which I will call it as dBp. P for perpendicular. So dBx, which is along the x-axis, and dBp, which is perpendicular to the x-axis. So these are the two components by means of which I have resolved my magnetic field dB at this point due to the current element ideal under consideration. Now for a moment we'll just ignore dBx, just consider dBp. So dB perpendicular acts in the upward direction. It is due to this current element. Now if I consider another current element which is diametrically opposite here. At this current element, if I assume that the current is flowing in this direction, right? Then this component, perpendicular component, acts in the upward direction. Now similarly, if I consider another current element which is diametrically opposite to this current element, then I will get another component at this point of the magnetic field which will act downwards, and these two will be exactly similar to each other in magnitude but opposite in direction, which means the magnetic field, or to be more specific, the perpendicular component of the magnetic field at this point due to this current element cancels out the perpendicular component of the magnetic field at this point due to the current element which is diametrically opposite to this current element. So if that is true, then at every point on this circular loop, I have a diametrically opposite point on the circular loop which will generate a equivalent perpendicular component of the magnetic field at point A, which are similar in magnitude but opposites in direction. So eventually, if I consider all the current elements along this circular loop, the perpendicular components, they all cancel out each other, which means when I sum up all the perpendicular components, the net summation is 0. So that leaves me to resolve or find out what the components along the x-axis are. So that's my only point, scope of interest over here. So now the dBp is summed up for the whole loop is equal to 0. the total magnetic field component at this point A due to this current element, the next current element, the next current element, and all the current elements along this loop. I need to do an integration of dBx for all the current elements. So before we do that, we'll have to resolve this phi angle so that I'm able to represent this phi in terms of my existing parameters that I've assumed. So if you just observe carefully here, this is 90 degrees. So if this is phi, this angle over here is 90 minus phi. Similarly, this angle between the displacement vector r and dB is also 90 degrees, which means this angle over here is also phi. So if this is phi, this is parallel to the radius over here, and this is a transversal cutting the two parallel lines, which means this angle here is also phi. So now, if I just take a simple cos phi, it is r divided by small r. And we already know small r is nothing but square root of r square plus x square by the Pythagoras theorem. So we'll just keep this in mind as we try to sum up all the values at point A for the magnetic field along the x-axis. Now if I consider a right angle triangle over here, I am interested in the component along the x-axis, which is dBx, and the hypotenuse is dB. So dBx can be written as dB cos phi, and dB cos phi we just resolve it as r by x square plus r square whole to the power of half. So I represent the square root as a power. Now what is dB? So dB I get from my resolution over here. So I put this value over here. So I get mu naught by 4 pi into I dl by x square plus r square into r divided by x square plus r square whole to the power of half. So simplifying what we previously got, we arrive at mu naught by 4 pi I dl r by x square plus r square to the power 3 by 2. Now this gives me the magnetic field along the x-axis due to one current element IDL that I have started my whole discussion with. Now if I were to sum up all the current elements along the circular loop, then the entire length would now translate to the circumference of the circular loop. So the circumference of the circular loop, you know, is given by 2 pi into the radius. The radius in this case is capital R. So 2 pi R. So that will be my summation of all the current elements along the circular loop. Which means the total magnetic field B is the magnetic field along the x component, which can be represented as the magnitude of the x component magnetic field multiplied by the unit vector I along the x-axis. So Bx will be my mu naught by 4 pi into I. Now instead of dl was only one current element. I am interested in the current elements along the entire circumference. So dl will get replaced with 2 pi r into one more r over here, capital R, divided by x square plus r square whole to the power 3 by 2. So further simplifying that will give me mu naught by 4 pi into 2 pi r square into I divided by x square plus r square to the power of 3 by 2. So 2 pi and 4 pi cancel out, and what I am left with is mu naught by 2 into I r square by x square plus r square to the power 3 by 2 into the vector form I cap. We need to put the unit vector represented by I cap. Now this is the magnetic field at any point A along the axis of the circular loop at a distance x from the center of the circular loop. Now as a special case, if I consider this very point, the center of the loop itself, then at this point the value of x becomes 0. So if I put x equals 0, B origin will be given by mu naught by 2 I r square by x becomes 0 if I am left with r to the power 2 into 3 by 2. So that on simplification gives me mu naught by 2 I r square by r cube. So r square and r cube, they cancel out each other partially, leaving me with B origin is equal to mu naught by 2 into I by R. So this is the special case of the magnetic field at the center of a circular loop carrying current I and having radius capital R. So here too I would need to put the I cap to indicate the direction of the magnetic field. Now mathematically we said this is along the x-axis, but if I were to find out at this point what would be the magnetic field due to the current flowing here, so that will be given by my right hand thumb rule. So if I hold this conductor over here, then my fingers are curled inwards, which means since the current is going upwards, my fingers are curled inwards, which means my current is at all points here. They are entering the board on the right side, emerging from the board on the inner part of the circle. Here, since the current is flowing downwards, my right hand thumb rule will show me that the magnetic field lines are entering inside the board to the left and emerging out from the inside. So effectively speaking, if I were to consider a circular loop, I'll have magnetic field lines going in an anti-clockwise direction as viewed from the top in the right side of the coil, and they'll be going in the clockwise direction as viewed from the top on the left hand portion of the loop. So this would be the direction of the magnetic field lines due to the magnetic field at the origin due to current flowing through the coil. So this would be a special case of the general equation that we just derived based on Biot-Savart law.